Air is composed mainly of nitrogen and oxygen, and these are diatomic elements. There are some elements that are found pure, but always two atoms bound together. Hydrogen is always H2. You never find just a single hydrogen atom. Nitrogen is always found as N2. You never find just a single nitrogen atom. Oxygen is O2. You never find just a single oxygen atom. It's always O2. It is always two atoms forming a molecule is how you always find oxygen. So they're always together. Fluorine, chlorine, bromine, and iodine, the halogens, always found two of them bound together. Diatomic elements can be separated. In water, neither hydrogen or oxygen is diatomic. Here we just have a molecule. All right, so a compound, like we just saw with water, a compound is a substance that contains two or more elements that are combined in a definite proportion by mass. For example, water is always H2O. There's always two H's for every oxygen in water. And so water is very different than oxygen and hydrogen. We can break water down back to oxygen and hydrogen by running electricity through it. And that's actually a really important reaction, because electricity is the only way to break water down into oxygen and hydrogen. And so that opened up the whole field of electrochemistry, when chemists realized that there were chemical reactions that could only be done with electricity. And so electricity is a unique energy source which can cause unique chemical reactions like this to occur. And the birth of electrochemistry gave us batteries, which we completely rely on today with our mobile electronics. Without good batteries, our iPhones wouldn't work, or they need to be charged every 10 minutes, and it just wouldn't be practical. And so the field of electrochemistry completely changed how we view electronics. Again, elements in compounds are always there in whole number ratios, H2O, or N2O5, P2O5, N2O. You always have small whole number ratios. Compounds fall into two general types, molecular and ionic. Molecular compounds have discrete molecules, like water. We can circle the individual H2Os. They're all discrete units of water. Ionic compounds come as huge aggregates. You never just get one sodium and one chlorine. It's always millions of them both. And so the formula for a molecular compound is actually what you would find in a single molecule. Water is H2O because each molecule of water is H2O. Sodium chloride is NaCl, not because you ever find just an NaCl, but that's the ratio you find it in. So if I find 1,000,000 of them, it's always in a 1-to-1 ratio. For every one sodium, there is one chloride. And so for ionic compounds, the chemical formula is just telling you the ratio at which you find these ions, because you're going to find them in massive aggregates. Chemical bonds hold H2O together. Molecular compounds are held together by shared electrons, which are covalent bonds. Ionic bonds are just held together by the attractive force that's natural to positive and negative charges. Molecules are the smallest unchanged individual unit of a compound. The least amount of water I can have is one molecule of water. And so just like an atom was the least amount of an element that I could have, a molecule is the least amount of a compound I can have. And you can break a molecule down to its atoms, but you destroy its identity. If I break water down into oxygen and hydrogen gas, I no longer have water. I no longer have the properties of water, because oxygen gas and hydrogen gas are totally different than water. Ions are charged atoms. Cations have a positive charge, and we call them cations because under an electric field, because they're positive, they move to the negative cathode. Because they moved to the cathode, they became cations. So positive ions are cations because under an electric field, they migrate to the negative cathode. Whereas negative ions are called anions because under an electric field, they move to the positive anode. So anions are the ions that move to the anode. And so the negative ions are attracted to the positive anode under an electric field. And so positive ions are cations, the negative ions are anions. So again, Positive ions, cations, negative ions, anions. More than 50 billion compounds are currently known. They each have unique properties. And so water and hydrogen peroxide. This we're going to see later is a great example of the law of multiple proportions because it's the exact same elements, water or hydrogen and oxygen, but they're in different ratios. Water is a 2-to-1 ratio of hydrogen to oxygen, whereas hydrogen peroxide is a 1-to-1 ratio. And as such, totally different compounds, complete different physical properties, different densities, different boiling points, different colors, and also very different chemical properties. A chemical formula will always tell us what's present. So we take sulfuric acid, H2SO4. This is telling us that one molecule of sulfuric acid has 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. Notice, no subscript 1 is used. If there's only one of something, it's just understood, but it's not written. If there was no sulfur there, you wouldn't put the capital S. Like, for example, there's no platinum or gold in this compound, so you don't see the symbols for platinum or gold. So by virtue of having the symbol there of sulfur, you know it's present. And so no subscript is an understood 1. All right. So again, sulfuric acid, 2 hydrogens, 1 sulfur, 4 oxygens. The symbols tell you which elements are present. The subscripts, the small numbers that are kind of lower, tell you how many atoms are in the molecule. If there's parentheses, if there's a subscript after the parentheses, it tells you how many of everything in the parentheses you have. So in calcium nitrate, I have 2 NO3s. This is CaNO3, NO3. I have 2 NO3s. I have 2 of everything that's in the parentheses. And the parentheses are useful so you don't get confused, because without that parenthesis there, you might think that was 32, which would be wrong. So, how many of each element is present in potassium phosphate? Well, I have a K for potassium, P for phosphorus, and O for oxygen. And I have a 3 for potassium. I have no number for phosphorus, which is understood to be 1, and I have 4 oxygen atoms. Magnesium hydroxide. Notice I have OH in parentheses with a 2, so I have 2 OHs. So I have 1 magnesium, but I have 2 OHs, so 2 oxygen atoms, 2 hydrogen atoms. All right, and here we see different compounds have different percentages by mass. Water is always H2O. No matter where in the world you find it, water is H2O. It's always 11.2% hydrogen and 88.8% oxygen by mass. Hydrogen peroxide is always H2O2, no matter where you buy it. It's 5.9% hydrogen by mass, and it's 94.1% oxygen by mass. The law of definite composition states that a compound always contains the 2 or more elements chemically combined in a definite proportion by mass, and it never changes. Water will always be H2O everywhere. Hydrogen peroxide will always be H2O2 everywhere. If you change the formula, you change the compound. The law of multiple proportions says the same 2 elements or multiple elements can combine in different ratios to form totally different compounds. That's especially true for carbon, hydrogen, and oxygen. All of the carbohydrates are carbon, hydrogen, and oxygen. So those 3 elements can combine in thousands of ways to form totally different compounds. And again, the same elements, when combined in different ratios, make totally unique compounds that are not like other ones. So methane, totally different than octane. Methane, CH4, that's natural gas, and it's a gas. Octane, C8H18, that is a fraction of gasoline. It's a liquid. And so again, they're both carbon and hydrogen, but they're in different ratios, meaning they make completely different, unique substances with unique chemical and physical properties. And that is the end of chapter 3.